Optimization of the catch-up shoulder for construction timetable implementation under external stochastic section. The specific nature of the construction industry does not allow adopting optimization methods from other areas of material production, but even methods specific to the construction industry under stochastic action have a limited area of practical applicability because of the complexity of the project and the planning detail. An approach based on the dynamics monitoring and adjustment of the schedule progress is adequately challenging for the project implementation. The quantitative characteristics of the contractor, the schedule, and its progress taking into account the relationship of economics and technological processes should be the basis for the development of current and strategic management decisions. The development of optimal decisions is possible only on the basis of the information model of construction. In this approach, not only local optimization, but also an efficient transfer of information and solutions between the heterogeneous participants of the project is possible. Relational database management systems are the optimal shell for information accumulation, updating, verification, and transfer. Decision-making and graphical analysis should be carried out in high-level mathematical packages, such to stage information models extended the practical application of BIM. The critical path method is one of the methods of reducing the influence of stochastic factor on project performance that is widely used in IECO practice. This method originated from a synthesis of the principles of Goldratt's constants theory and Deming statistical approach. This method is based on the concept identifying critical paths and damping them a priori. The first critical path models built under the assumption of complete certainty of time and cost of work have shown unsatisfactory results in a large number of practical applications. The exponential increase in the prediction error of a dynamics of a system undergoing stochastic influences is not specific to the AECO industry. This effect is a particular case of general patterns inherent in complex systems of any nature. The information needed to calculate to the time dependency of the type index is fully defined by matrices of dimension nxm, where n number of NR types and m number of planning intervals. Further, in all matrices and vectors, the index I 1, 2 to n will number resources and index j 1, 2 to m will number the planning and monitoring interval. Since the system stability to external stochastic effects is determined by the degree of resource reservation, it is necessary to define matrices describing the characteristics of the contractor and the profile of resource utilization during the implementation of the calendar plan. The matrix DIG, whose components are defined by the following equality. The integral degree of I resource scarcity is determined by averaging over the planning period. The analysis of the parameter value di make it possible to determine the possibility of resource maneuvering and should be carried out of the planning state. The time periods when such a maneuver is possible are determined by analyzing the dynamics of the scarcity index DIG. Graphically, this analysis of individual resources is shown in Figure 1. The global analysis of all projects NR requires a 3D scarcity index mapping. An example of such a mapping for a set of specialists is shown in Figure 2. In Figure 2, the resources are ordered by the degree of scarcity at the time of the construction start. The step of the equal index lines D. You can clearly see the area's poor resource utilization at the beginning of the planning period and the areas of resource maneuver capability for the majority of the resources. The total utilization efficiency EGI of the I reserves for the period from the start of the planned use of the resource to the time of the current monitoring TJ is determined by the following formula. When implementing the estimation algorithm in software, it is easier to use a recurrent formula instead of closed formula 3, which explicitly take into account the information accumulation mechanism. In this case, the algorithm for calculation efficiency, this formula, is expressed into the following way through the plain values and monitoring results and initial values of this formula. The inability to reserve the relevant NR leads to the need to pay maximum attention to monitoring them and dynamically optimizing their utilization profile. It is possible to solve this problem with the help of the dynamic index of personnel and equipment use type defined by the formula. Optimization of high-cost projects in the course of which unique equipment is used requires a more detailed description of the dynamics or NR utilization. The unique resource utilization index URIGI expressed through the scarcity and efficiency indices solves this problem for the following way. This mechanism can be described by the following resource relation, which makes it possible to express the index URIGI for the ith resource as g's moments of time throughout its values at the moment of monitoring in the form. The two-dimensional nature of the index URIGI results in the need for a graphical representation in 3D format. An example of such a mapping is shown in Figure 3. The implementation of this algorithm is reduced to the formation of basic structures and the formulation of methods for hierarchical constructions of structures of higher ranks. In the formed information monitoring model, all structures are matrices whose rank is determined by the number of NRs and the number of planning intervals. The formats of the elements are determined by their practical content.